Identification. Start with, concrete gives us an ability to recognize some of its hazards because it's cracked or it cracks. Normally, concrete cracks with very little significance due to shrinkage, due to temperature effects, and as one of my old former employers used to say, if it's not cracked, it's not concrete. But the kind of cracking that we look at in urban search and rescue is the distress cracking, the diagonal cracking in beams and vertical cracking, and the X cracking in walls that we discussed in the first section. And here's again the same kind of a picture. The importance is if these cracks change. We know they're going to occur if the structure has been loaded severely. They really just indicate that it's working. But what we want to know during the during the rescue phase and recovery phase is, have they changed? Is the structure deteriorating? And is it a greater danger to us? Some examples from the 880 freeway of some cracks. Mostly here, they're diagonal cracks in the beam. And yes, there's a very large diagonal crack at the right in the column, which indicated some of its weakness. But the ones that I'm trying to illustrate here are those in the beams. Here are what the crack patterns will look like in a shear wall. The classic X cracking normally occurs between the openings. Sometimes it'll occur over the openings where the stresses are very high due to earthquake loading, also due to blast loading. Although in blast loading, the cracks may only be in one direction because the blast force may be only in one direction. So once we see these cracks, we can make a judgment as to the capacity that's left in the wall. In the case of a reinforced concrete wall where we know there's reinforcing, we get the clamping action of the weight of the wall on the jagged surface of the crack. There's also friction, and there's also the fact that the rebars stick through the crack and form little dowels. In cases where the wall has degraded, we'll almost be able to see through the crack. There'll be low friction, and the bars may be offset, and so in that case, one would make a different judgment as to the risk involved. And of course, risk is part of what we do in urban search and rescue, and risk is always assessed against the reward, so that in the case of quickly getting to live victims, we might be willing to take a higher risk, whereas in the case of the recovery mode where we're being quite safe, we probably wouldn't take as great a risk. And so that's what we engineers help make value judgments with, and that's why knowing things about these hazards is quite important. Here's some samples of some cracks. Actually, these cracks are not really that detrimental in this building. This building was abandoned. It's a hospital in Southern California, built in 1925 from the Northridge earthquake, but just gives you an idea of what some of the cracks look like. And again, you'll notice they're all X. Some of them have concrete that's fallen out. Obviously, those are a little bit more degraded, and some do not. Just an example. Different case when you're talking about unreinforced masonry, because you don't have any reinforcing steel, you don't have much in the way of friction. You get this crack that follows the sort of the mortar lines between the bricks. Sometimes it'll go through the bricks. But once a masonry wall is cracked, it's pretty much not very useful anymore and becomes quite dangerous. Here's an example of actually a good performing unreinforced masonry building that has been tied together, or so-called retrofit, for occupancy in California, and survived the Northridge earthquake actually quite well. So all the occupants that were in the second story got out. No one was hurt. The building was destroyed afterwards or deconstructed afterwards because it's too expensive to repair. But little things you can notice there in the right-hand picture, how buildings operate. You'll see there's a fairly large crack that occurs near where the roof intersects the wall, and that's how the building was trying to resist the wall pushing against the roof. Not quite strong enough to work its way without doing a large crack, but nonetheless it stood up there, just to give you some idea of how these things work together. So when we look at structures, building structures and other structures, we want to look for falling hazards. Obviously, those are going to be something that will cause additional casualties, collapse hazards where spaces will be more confined. And of course, then there's other hazards that the hazmat folks will point out to us from chemicals either placed by terrorists or just mixed together normal household chemicals. And when we make judgments about structural hazards, we never can be precise. We do the best we can. Because it's a partially collapsed structure, it's very, very complicated, almost boggles the mind when an engineer first sees it. Our structures obviously have come to rest. In coming to rest, they've expended a lot of energy, and so in stopping the collapse, if you will, the structure has absorbed energy. We know it's sort of stuck together in one way or another. It's very disorganized, but in the case of earthquakes, we always have the threat of aftershocks. And so we know from past experience that structures collapse in aftershocks, and so we have to keep that always in our minds and always prepare for that eventuality. Now we're going to show a series of pictures of various types of buildings, starting with the simplest, which is a light frame house. Looking at, and each one of these pictures has an idea of what the hazards are. In the case of a house, probably the biggest hazard could be fire. Because once a house is shaken, the wood is exposed, and gas pipes may be ruptured, and so we have the presence of gas, we have the presence of a lot of fuel, and those things need to be taken care of. The gas needs to be shut off and tagged out as soon as possible. The other hazards normally are things that are not consistent with the wood structure itself, like heavy clay tile roof and the chimneys. Chimneys are historically are sort of the poorest performing part of any house residence that's built out of wood. So here are some examples. Upper picture looks like a badly racked structure. Is that structure a good risk to enter? I would say on a short-term basis, absolutely yes. But again, you limit the entry, only a few people in or one or two, and then with others outside to help them. Would I look for another entry besides the one I see there? Absolutely. But if there was someone down and it was, determined that one needed to remove a viable victim, we would mount an operation to do that. Same thing with the structure below. The other thing that one needs to know about these structures, that once they've come off their foundation or shifted, that they would contain very badly sloped and broken floors with pieces of wood sticking up and nails that are sticking out and all kinds of tripping and falling hazards and perhaps broken wires and the potential for electrocution. And so, again, all those things need to be handled before you enter the structure. The electricity needs to be turned off. A special warning there is that when earthquakes first occur, normally all the electricity gets turned off because the system goes down. And we in search and rescue have to make doubly sure that we remember, even though everything is off, the whole system may come back on when we're in a structure. So we have to make sure that in each case that at the meter, the proper lever has been pulled and the electricity has been turned off. That hasn't always been the case. So here's a picture of some chimney failures, and whether it's a one-story, two-story, or whatever story chimney it is on a wood house, whether they're code-approved ties or not, I'm here to tell you that that is a dangerous situation, and unfortunately, in every earthquake, many, many chimneys fall. Once they fall, they're relatively easy to deal with because they can be avoided or they can be removed, and we want to make sure that we don't get in their way. Likewise, roof tile in these two pictures, the upper one is actually from an earthquake, Northridge, and the lower one is from a hurricane. That's Iniki on the island of Kauai. I might say that the lower one is probably safer from a standpoint of search and rescue because you don't expect a second hurricane. In the case of the Northridge, one would expect aftershocks, and we don't want to fall victim to falling tile. All right, from here, we're going to start talking about slightly larger structures, and this is the multi-story wood frame structure. And by the way, this picture and all the subsequent pictures and the information about what to look for can be found in Section 1 of the Shoring Operations Guide, or the SOG, that is available on disasterengineer.org. And if you're in a FEMA task force, your task force has a number of these publications, a number of copies of this publication for your use. So with this kind of structure, the things that we would look for again are, it's a wood structure. In this case, we're seeing it's badly racked. So the first thing that I would want to know is what kind of sheathing does it have on the first story? Is it fairly ductile sheathing like plywood, and I can make a judgment on that, or is it just stucco over some kind of gypsum sheathing that's black board and I can stick my hammer right through it? I can make a judgment as to what might happen in the next aftershock. The other thing that I would be concerned about would be if it has heavy roofing, or looking at those balconies and knowing how people live. We have usually heavy plants, we have barbecues, we have all kinds of things on our balconies, and one would want to make sure that we didn't get ourselves in the way of a falling hazard from one of those. Here's some examples. Actually, it's the same example of a two-story apartment house with brick facing. The most important thing here is, the important hazard is the brick veneer that can kill us if it falls off in an aftershock. A large amount of it has already fallen off. And in this particular structure, there was a side of it that didn't have any veneer, so obviously that would be the side that we would enter from if there were any victims. Another thing that's unique about this structure, if you look at the lower picture, you can see that at the very lower left, that the footing has offset on the left-hand part of the structure, and that offset didn't read, or you couldn't see it from the ground. It didn't read up into the structure until you got up on an aerial ladder, and you could see that the roof had parted some 20 or more feet to the right. So sometimes one has to not only go all the way around the structure to assess it, but if there was an availability of an aerial ladder, to look over the top of it. This is an example of a collapse that occurred in a relatively small aftershock in the Loma Prieta earthquake. The upper picture is the four-story structure with the garage doors closed that are keeping it from collapsing perhaps. But following the earthquake on a Tuesday, this is a Saturday, and there was the 5 aftershock, and you can see in the lower picture that you now have 3 stories sitting on the ground, where the second story is at the ground level and the first story is pretty much collapsed underneath it. Very small, very vulnerable structure, very small aftershock, complete collapse. And at this point, I think it's fair to say that after the aftershock, the structure is pretty much at rest. Now, in this case, because the structure had been abandoned by then, or all the people removed, but it just serves as an example that aftershocks do collapse buildings, even relatively light wood ones. This is the picture then of a heavy wall kind of construction. Here we have all kinds of vulnerability, including the fire and gas being on, electricity being on, kind of thing that needs to be assured that it's turned off. The walls in the masonry building will become cracked, and the remaining walls can more easily fall in an aftershock, I think it's fair to say. The other thing that happens is that as the building tries to act like a box, what happens is that as the loads are generated in the roof structure, the roof structure plane, if you will try to resist the forces, and it finds the corners usually as the hard point of its resistance and will tend to knock the diagonal corners out. And you can see in the upper left depiction there of the diagonal corner being badly cracked and possible to be knocked off. And I'm going to show some slides of that. Here in the upper slide, you can see that diagonal line where that whole section of wall has the potential of being knocked out. It's not something that's necessarily easy to see at first, and one has to, again, go around the structure completely to make sure of these hazards. The lower picture, the hazard is quite obvious. What started out as X-cracking ended up with a whole section of the wall falling out. This is unreinforced unit masonry, concrete unit masonry that was in the Kalinga earthquake. Here's a couple of other examples. The upper example is an aftershock collapse. The parapet of the building in the background collapsed on the building in the foreground, which was a light metal building, and collapsed it in an aftershock. The lower picture, it's obvious to see that upper piece of concrete, the header over the opening, is very, very vulnerable and wants to be avoided if there is any need even to be in the structure. The other thing that happens to all of us when we are in an incident that lasts for a multi-number of days, we tend to get a little tired. We might even tend to get a little numb if we don't have good safety officers that are reminding us every day about our PPE, our protective equipment. And this just depicts a couple of 3 or 4 fellows standing having a conversation with their morning coffee without any protection in a very, very vulnerable neighborhood, something that we certainly don't want to do. This is showing some of the issues with the tilt-up building, remembering that it's the interconnection between the walls and the roof that are the issue to us. so that all those connections of the remaining part of the structure, let's say we're having to get in the structure to find victims, we want to make sure that all those other connections are adequate, and there is a sort of a special connection inside in the length of a beam called a hinge connector, which is shown a couple of diagonal lines where one, by just looking up and seeing the change in coloration of the wood, you can tell if something is pulled out by the fact that the wood color will be much lighter than the color of the wood that has been exposed to the atmosphere for years previous. Here's an example of what to do in a collapse in a tilt-up building. In this case, the wall is completely disconnected from the roof, and but the wall has not fallen. The roof is being supported by the aluminum storefront, certainly not designed to do that, but it's holding it up. And let's say there's a victim where we've got a little V. One would have to make some judgments about what to do with the structure in the way of mitigation to be able to remove the victim. As an example, if the victim could be removed within a few minutes or less than a half an hour or so, one might do nothing more than minimize the exposure of only having a few people getting to the victim and having someone monitoring the rest of the structure. If it took a considerable amount of time, then one might have to look at shoring and raker shoring the wall and perhaps vertical shoring the roof. So it always depends on the victim. It depends on how long it might take us to get to the victim. It depends on the risk we're willing to take for a live victim versus the risk we're willing to take for removing unviable victims. So in summary, structures come to rest. That doesn't mean that they're stable. It means that they're at rest. They've experienced lots of movement, perhaps. They've sort of been collapsed into a shape, and so that's absorbed a lot of energy. That's a good thing. On the other hand, if we have aftershocks or strong winds, that can change that stability, that at-rest condition. Also, when we remove things or change things, we may change the situation and cause the structure more to move a little bit. So we do the best we can, and again, it all comes back to risks and rewards, and that's what engineers do for the Urban Search and Rescue Program. We try to assess the risks and put some kind of a handle on what they are. So it all works in concert for the search and rescue effort. We've used the term stability throughout this presentation a little bit, and just wanted to give you a sort of graphic. The stability is defined. A stable system is one that will come back to its original system. We don't normally deal with those. So the picture at the left, obviously, that's a little bit of a ball that always comes back to the middle. The picture at the right, that ball never comes back to the middle, and that's sort of what we deal with. Please obtain a copy of the U.S. Army Corps of Engineers Shoring Operations Guide, or SOG, on disasterengineer.org.